Hello, I'm Ellie Pinches, an Education Officer at the Royal Meteorological Society. In this series of short films, we're going to be covering some of the background information that teachers may find useful if they're teaching weather and climate at secondary level, and specifically if they're using our weather and climate teaching guide with accompanying classroom resources which can be found on our website, MetLink. There's links in the notes below. In this film, I'm going to be looking at polar climates. Some of the most extreme seasonal variations in weather can be found at the poles, driven by the variations between polar night in the winter and 24 hours of daylight in the summer. The global atmospheric circulation, which we looked at in Chapter 4, suggests that polar regions should be dominated by sinking air, high pressure and clear skies. The Arctic is the source for any polar continental or maritime air reaching the UK. According to the Köppen-Geiger classification system, which is the focus in Chapter 5, polar climates are defined as the warmest temperatures of any month being below 10 degrees Celsius. Polar climates are further divided into two types, tundra climates and ice-cap climates. In tundra climates, the warmest month has an average temperature between 0 and 10 degrees. These climates occur on the northern edges of the North American and Eurasian landmasses and on nearby islands. Ice-cap climates are dominant in Antarctica and inner Greenland. Monthly average temperatures never exceed 0 degrees Celsius. In the centre of the Antarctic, it can truly be too cold for snow. To explore why, we need to revisit what the requirements for snow are. Requirement 1, moisture. There must be water vapour in the air for clouds to form. In the UK, surrounded as we are by relatively warm sea, this is rarely a problem. As water warms up and cools down more slowly than land, the sea around us stays at a pretty constant temperature all year round and is a constant source of water vapour into the air. It can be too cold for snow in the centre of large land masses such as Eurasia, Antarctica and North America, where the wind has not encountered liquid water from which water can easily evaporate. It is really too dry for snow because it's too cold. It's so cold that the rate of evaporation from the lakes and rivers, which may be frozen, is very, very slow. This image from earth.nullschool.net in February 2020 shows precipitable water, which is the total mass of water contained in a column of atmosphere over a given area. In this case, there's just 600 grams of water in the entire depth of the atmosphere over each square metre on the surface in the green circled area, and this is really low. Requirement 2 for snow, cloud. For cloud to form, the rate of evaporation must be lower than the rate of condensation. Evaporation and condensation are actually going on all the time, but the rate of evaporation falls as it gets colder. So clouds can form when the air cools. There are several possible mechanisms for cloud formation. Number 1. Cloud forms when warmer air meets colder air at a front, causing it to rise. As the air rises, the pressure falls and so the air cools. This is known as adiabatic cooling. We can get snow when polar continental air meets polar maritime air at a front in winter. The cold polar maritime air is forced to rise over the even colder polar continental air, leading to cloud and snow. Number 2. Cloud forms when air from somewhere cooler than us, for example the Arctic or Siberia, approaches the UK. It is warm from below as it travels over relatively warm land or sea, which causes it to rise and cool. This is the most common source of snow in the UK. Number 3. Another mechanism is when air is forced to rise over the coast, hills or mountains, and as it rises it cools. This mechanism can add to or enhance the formation of clouds by either of the other mechanisms mentioned. And number 4, if the ground cools overnight, the air in contact with the ground can cool to the temperature at which cloud forms. This is fog and is not likely to produce rain or snow. Requirement 3 for snow is temperature. It has to be cold enough for the cloud droplets to grow as snowflakes and to not melt as they fall through the atmosphere and down to the ground. To see whether this is the case, forecasters look at the 528 decameter line, which you may hear some people calling the 528 dem line. This line shows where the vertical thickness of the bottom half of the atmosphere by mass is 5,280 metres. In other words, the vertical distance between the 1000 millibar height, somewhere near the ground, and the 500 millibar height, somewhere in the middle of the troposphere is. As warm air is less dense than cold air, the colder the air is, the less thick the atmosphere is, the smaller the distance from the ground to the 500 millibar height line. If we are north of the line, where the thickness is less than 528 decameters, then any precipitation can fall as snow. If we're south of the line, where the thickness is greater than 528 decameters, then it will rain. If you look at the surface pressure forecast charts on the Met Office website and you go to more than 24 hours in the future, the thickness lines are shown. The 528 decameter line is shown as a blue dashed line and the thicker, warmer 546 decameter line as a green dashed line. Alternatively, look at the GFS charts, which you can navigate to in the Charts and Data menu on NetWeather. Select HDT 500 to 1000 from the Choose Chart Type menu. This clearly shows that the thickness is greater for warmer tropical air and smaller for the cooler polar air. In wintertime, polar regions are incredibly cold due to the lack of sunshine. Although surface pressure may be high, associated with the global atmospheric circulation, the temperature contrast between the Arctic and more southerly latitudes leads to very fast winds high up in the atmosphere. This results in a huge low pressure system spinning anti-clockwise above the Arctic and clockwise over the Antarctic, known as the Polar Vortex. From the side, you would be able to see this huge system reaching from the upper troposphere all the way to the stratosphere. The Arctic polar vortex can change its shape, as seen in the schematic diagram. While a stable polar vortex confines cold air to the Arctic, an unstable or wavy polar vortex may cause cold air to spill further south. This is what we experience as cold snaps. A so-called sudden stratospheric warming event can lead to such an unstable polar vortex. A disturbance in the polar vortex leads to a sudden compression and warming. It rapidly weakens the polar vortex and causes it to wobble. If these wobbles split off, they can make their way towards Europe and bring cold Arctic air across Europe. The 2019-2020 Northern Hemisphere winter was an example of a very stable polar vortex. In the Southern Hemisphere, both Antarctica and the surrounding Southern Ocean are much more symmetrical than the continents in the Northern Hemisphere. This leads to a much more stable polar vortex and consequently lower winter temperatures at the pole. In general, climate change is more rapid in polar regions, particularly the Arctic, than in the rest of the world. This is referred to as polar amplification. It's mainly due to the positive feedback mechanisms there. For example, as the temperature warms, sea ice melts, exposing the ocean below. Water reflects less sunlight than ice, so more light and heat from the sun is absorbed as the ocean is exposed. This further heats the polar regions. Other contributing factors include the transport of heat from the tropics to the poles by storms in the global atmospheric circulation, changes in the cloudiness, and other positive feedback mechanisms through increasing water vapour in the air. If you would like more information on polar amplification, there is a link in the text below. Currently, the Arctic is warming faster than the Antarctic. This is partly due to the hole in the ozone layer over Antarctica. As the ozone recovers, Antarctica will warm faster. Changes in Arctic temperatures may have an impact on mid-latitude weather, which is summarised in this diagram. There is some suggestion that with a warmer Arctic, the polar vortex will be weaker. Ozone is a naturally occurring gas. Over 90% of the ozone in the atmosphere is found in the stratosphere, between 10 and 50 kilometres up in the ozone layer. There, it absorbs UV radiation from the sun, which would otherwise reach the Earth's surface with harmful effects, including the destruction of chlorophyll in plants and a greater chance of skin cancers and eye cataracts in humans. In the winter, the land and air inside the Antarctic Circle does not receive any solar radiation at all and cools by emitting infrared radiation to space. As it does so, the air in contact with the ground is cooled by conduction and convection. As the air cools, it sinks, and the air pressure at the ground is relatively high. Conversely, the air pressure in the upper atmosphere is relatively low, and it draws in more air. Because of the rotation in the Earth and the Coriolis effect, which we've looked at a lot in Chapter 8, this sinking air develops a clockwise swirl. A vortex, known as a polar vortex, develops, and wind speeds around the vortex may reach 100 metres per second in the middle to lower stratosphere. To give this speed some context, a low pressure system in the tropics is termed a hurricane when surface wind speeds reach 30 metres per second. This vortex isolates the air inside, making it very hard for it to mix with air outside the vortex. The very low temperatures that can be reached in the centre of the polar vortex are low enough for polar stratospheric clouds to form, which are sometimes called nacreous clouds. Polar stratospheric clouds form at temperatures below -78 degrees Celsius. In July and August, temperatures in the Antarctic lower stratosphere can reach -90 degrees Celsius. Nacreous clouds can sometimes be seen bright in the night sky because they are high enough to be illuminated by the sun long after sunset at the ground. Chemical reactions on the surfaces of the cloud particles in the winter form molecules which destroy ozone as soon as the sunlight returns to the stratosphere. The rate of ozone destruction can be 2 to 3% per day in late winter and early spring. However, when temperatures increase in spring, polar stratospheric clouds no longer form and the intense period of ozone depletion ends. As the Antarctic slowly warms through the spring, the polar vortex breaks down and the relatively high concentrations of ozone that have accumulated at the edges of the vortex through the winter get mixed into the Antarctic air, rapidly raising the levels up again. The ozone hole disappears by December. The greenhouse effect and the ozone holes are frequently confused. Although some ozone-destroying gases, such as CFCs, are greenhouse gases, the process that results in the destruction of stratospheric ozone are entirely separate. However, at a deeper level, the greenhouse effect and the stratospheric ozone are linked in several ways. Greenhouse gases such as water vapour, carbon dioxide and methane in the troposphere absorb outgoing infrared radiation, or heat from the Earth, warming the troposphere. This in effect means that the less heat reaches the stratosphere, which then actually cools as the troposphere warms. A cooler stratosphere would extend the time period over which polar stratospheric clouds are present in polar regions, and as a result might increase winter ozone depletion in the lower stratosphere. Another effect of increasing greenhouse gas effect is the more water vapour gets into the stratosphere, again increasing the number of polar stratospheric clouds. To complicate matters, because ozone itself is a greenhouse gas, as the amount of ozone in the stratosphere begins to recover, it will in fact contribute to the warming of the Earth. As well as emitting light, heat and ultraviolet radiation, the Sun emits charged particles. Solar flares and coronal mass ejections, CMEs, send a plasma of charged particles towards the Earth as the solar wind. Forecasts for such space weather are now routinely made because of their potential impact on satellite-dependent communications and terrestrial power lines. In the polar regions, a CME interacts with the Earth's magnetic field to give us the auroras. Space weather may have an impact on the Earth's weather too, making it generally cloudier and generating more lightning strikes. In the next film, we're going to look at hot desert climates.